SAPA Extrusions is the world's leading producer of extruded aluminum products. Headquartered in Oslo, Norway, we employ over 23,000 people worldwide. In the Americas, SAPA operates 25 locations across the United States, Canada, Argentina, and Brazil. Our products include extruded aluminum solutions for virtually every market: building and construction, automotive, solar and renewable energy, thermal management, fabrication and machining, commercial transportation, and more. SAPA aluminum is the strong, lightweight, renewable material behind many of today's most innovative product designs. Aluminum extrusion is the process of using high pressure to force aluminum material through the shaped opening of a steel die, creating an extruded aluminum profile or shape. In brief, the heated aluminum billet is placed into a steel cylinder or container, then forced through the container by a ram under as much as 100,000 pounds per square inch of pressure. A die stack at the far end of the container holds the opening through which aluminum is extruded to form the desired shape. Once the material is extruded, it will be cooled by quenching, stretched for straightness, sawed to working lengths, and then inspected. Finally, the extrusion is aged to desired temper, tested for physical and chemical properties, further fabricated as required, and packed for shipment. Let's look at each step more closely. The extrusion process starts with the casting of aluminum alloy logs, which are made by melting high-purity aluminum along with purchased and in-house scrap and alloying elements, such as magnesium, silicon, copper, or manganese. For example, the primary alloying elements added to 6063 alloy are magnesium and silicon that form a compound called magnesium silicide, which gives the alloy strength. Here the furnace is being charged with aluminum. It is here that we introduce alloying elements to achieve the desired strength or other material characteristics of the alloy. The carefully controlled casting process uses spinning rotors to remove the unwanted gases. The liquid aluminum is also filtered to remove impurities. During the casting process, the grain of the metal is refined to desired characteristics. Molten aluminum pours out the back of the furnace and into a filtration box that removes the gases and impurities. After it leaves the filtration box, the molten metal travels through the trough and into the casting unit. Here we are casting 15 logs at one time. The logs can range in length from 20 to 30 feet. With our own in-house casting facilities, SAPA enjoys several important advantages versus purchasing cast metal from other sources. First, we have optimal control of alloy chemical composition for superior machinability, formability, and specific end uses. Second, we can offer more alloys for different industry needs and provide metallurgical support with matched alloy grades for customers. Finally, in-house casting allows us to offer expedited delivery of specialty products, thanks to our control of cast extrusion billet availability. Once the aluminum logs are cast, the next processing step is homogenization to improve the microstructure of the cast log. Homogenization is a high-temperature thermal process used for optimal extrudability and extrusion characteristics. After the cast logs are cooled from homogenization, the logs are then cut into shorter lengths, called billets, which can vary in typical lengths from 20 inches to 50 inches long, depending on the finished part length. Prior to extruding, we reheat the billets to a temperature that makes the material malleable, and in the case of 6000 series alloys, to achieve the desired strength requirements. Depending on alloy temper requirements, the temperature may be 800 to 1000 degrees Fahrenheit. It is critical that the billet is heated uniformly throughout using gas-fired furnaces or induction heating. Besides the billets, we also need to heat the dies to a suitable temperature. Extruding hot billets through a cold die is dangerous and can result in a broken die. Here, a heated billet is being loaded into the press container on a billet charger. The ram pushes the billet into the container and continues to push while the aluminum begins to exit through the die opening. Here, extrusion is emerging from the front of the press. The material temperature is still roughly 1000 degrees Fahrenheit. Unlike other metals, aluminum does not change color when heated to high temperatures. The specialized dies and extensive tooling required for each press and specific shape are often designed at our own in-house facilities. SAPA can design, build, and maintain the complete range of tooling needed for our presses, which helps to reduce lead time on customer orders. There are two distinct aluminum extrusion methods. Most common is the direct extrusion method, where the material is pushed by the ram through the container and material exits through an opening in the stationary die. With the direct extrusion process, the center of the billet flows faster than the metal at the perimeter. That is because of the tremendous friction at the container walls. Friction is a major energy cost of extrusion. Some calculations have friction accounting for half of the total energy drain on our business. Friction also robs die face pressure and can vary extrusion temperatures, which in turn affects dimensional control of the finished extrusion. The second extrusion method is indirect. With indirect extrusion, the billet is still inserted into the container. However, the die is placed within a hollow stationary ram. In the indirect extrusion process, the entire container and billet move together over the hollow die stem, and material is forced through the die opening. With this method, we eliminate the majority of the friction on the container walls, which results in more uniform extrusion temperatures and less pressure required for the extrusion process. There are several key differences between direct and indirect extrusion that makes them valuable for different needs. Indirect extrusion requires less die face pressure, while it minimizes the friction and heat to allow for more consistent dimensions, properties, and grain size. There is a sacrifice of overall shape size, however, because the special tooling must fit inside the hollow ram. Since the outside of the billet becomes the outside of the extrusion, the billets must be scalped to remove the outer surface. Scalping removes a shaving of material from the outer diameter of the billet. Direct extrusion allows for larger profiles with no need to scalp billets and better surface quality on the finished profile, but at a higher energy cost. Dimensional consistency, material properties, and grain size are harder to control with a direct extrusion process. Regardless of extrusion method, the next step in the process is to get the heat out quickly. Quenching is one of the most critical steps in the entire press heat treatment process. Every press includes a series of fans, a water quench box, water spray, a tank of water, or in many cases a combination of several quench methods. By quenching the extruded material, we lock the elements and phases that are in the microstructure of the alloy to achieve the desired strength requirements. Of course, whenever you introduce rapid cooling into hot metal, distortion can occur. The stresses formed cause the metal to twist and bow. We overcome that by placing the extruded length into a stretcher to control straightness and for stress relief. The typical stretch percentage for T6511 temper calls for a 1 to 3% stretch of the extruded length. After stretching to control straightness and relieve stress, the extruded length is cut to required finish or rough cut lengths and inspected to assure the dimensions meet the required tolerances using calipers, micrometers, straight edges, gauges, or other inspection tools. For some complex profiles, a comparator or coordinate measuring machine may need to be used to accurately measure the dimensions. Additional tests that may be performed to verify mechanical properties include metallographic analysis, hardness testing, tensile testing, or bend testing. Once the material is confirmed to be within the required dimensional tolerances, it is placed in a rack and loaded into aging ovens. A typical aging cycle can be 6 to 8 hours at an elevated temperature, which brings the material to its full hardness, such as T6 temper. Once aging is complete, the finished extrusion can be sent for any final fabrication steps before being packed to ship to the customer. SAPA offers a wide range of fabrication and finishing capabilities, from punching or drilling to CNC machining and fusion or friction stir welding. We can also paint or anodize the completed extrusion product. SAPA Extrusions is the world leader in aluminum extrusion, with more facilities producing extruded aluminum than any other company. Our decades of experience make us experts at both direct and indirect extrusion. Customers can rely on SAPA for not only quality product, but also the engineering and design expertise to develop leading-edge customer solutions. Strong, renewable, lightweight extruded aluminum from SAPA is changing industries around the globe. For additional information on our capabilities, please contact a SAPA Extrusion North America representative.